3 marks. That is so often the exact tiny margin separating your current Cambridge physics grade from the one you actually need. Today, we're mastering electric charges for the 0625 syllabus, but more importantly, we're mastering exactly how the examiner wants you to write about them. Literally, 3 marks. That's the exact number that frequently separates a current grade from your target grade boundary in the final exam. And honestly, it is incredibly frustrating to miss out on a higher grade simply because of your phrasing. So let's dive right into this and see exactly where those marks usually vanish when students tackle questions on electrostatics. Okay, does this quote look familiar at all? Rubbing a polythene strip makes it charged, so it pushes the other one away. This right here is a painfully common, flawed learner mistake that literally bleeds those crucial marks. Now, to a student, this sounds completely fine, right? It describes the physical action and it describes the result. But to the Cambridge examiner, oh no, this is simply not enough. And here's the exact problem with standard revision. A student writes, it gets charged. The result? 0 marks. Nada. Knowing the general idea in your head is totally useless in the exam hall if you don't have the specific wording. Ordinary revision fails because it just focuses on memorizing facts rather than structuring those facts to meet the mark scheme's exact demands. Which brings us to the top-band framework. Let's see how this foolproof step-by-step method essentially forces the examiner to give you full credit. So the secret sauce here is breaking your answer down into these 4 sequential steps. Step 1, identify the core concept. Step 2, provide the practical evidence or data. Step 3, apply the scientific reasoning that links them together. And Step 4, honestly the most important one, lock it all in with precise examiner wording. This framework right here is what transforms vague, everyday thoughts into those top-band Cambridge answers. Now, in a moment, I'll show you the examiner clue regarding the gold leaf electroscope that changes the answer completely. But first, we absolutely need to master the framework that actually makes that clue obvious to you in the first place. Let's jump into steps 1 and 2, concept and evidence. We're going to build this using the foundational concepts of electrostatics. So let's look at the fundamental mechanism at play here. When a material is rubbed with a cloth, friction transfers electrons. You've got to remember, electrons carry a negative charge. If the material gains electrons in this process, it becomes negatively charged. Makes sense, right? If a different material loses electrons when it's rubbed, it becomes positively charged. That is your core scientific concept. It's not magic, it is literally the physical transfer of negative particles. And here is the exact evidence you need using the Cambridge syllabus materials: polythene and cellulose acetate. If you take 2 rubbed polythene strips and bring them together, the result is that they repel. However, if you take a rubbed polythene strip and a rubbed cellulose acetate strip, they attract. This table represents the physical, hard data you absolutely must use to back up the concept of positive and negative charges. Now, to test these forces, you can't just hold both strips in your hands like magic wands. You need specific equipment. We're talking a paper stirrup, thread, and a retort stand and clamp. This precise setup allows you to support one of the strips horizontally in the stirrup, suspended by the thread from the stand. This means it's completely free to swing when another charged object is brought near it. Okay, so here is a crucial point, and seriously, pay close attention because this is a critical methodology tip directly from the source that students forget to write all the time in practical questions. The suspended strip must be entirely stationary before you bring up the second charged strip. If you bring the rod up while the suspended strip is already moving, your evidence is completely invalid. You won't be able to tell if the movement is from momentum or from actual electrostatic force. Moving right along to steps 3 and 4, reasoning and examiner wording. We've got our concept and evidence, now we need to lock in those marks. Here is your essential scientific reasoning. It's just a fundamental law of physics. Like charges repel. This simply means 2 negative charges, or 2 positive charges, will always push away from each other. Conversely, a negative and a positive charge, unlike charges, will attract each other. Whenever you describe the movement of those strips in the paper stirrup, this exact law is the scientific reasoning you must explicitly state. And this is how we upgrade our language to match the mark scheme. Look at the weak wording on the left. It gets charged. That tells the examiner literally nothing about your scientific knowledge. Now look at the right. Electrons transferred by friction. Boom. That is the exact phrasing the examiner demands. You aren't just saying a charge magically appeared, you're proving you know exactly what moved, the electrons, and exactly how they moved, by friction.
All right, time for an interactive examiner challenge. Can you spot the error? Let's test your active recall. Take a look at the sentence on your screen. This is a real, typical student answer describing the practical experiment. I rubbed the plastic and brought it near the swinging strip. I want you to spot the methodological error in this sentence. Think back to that critical experimental tip we discussed just a few moments ago. What exactly did this student do wrong?
Okay, let's see if you caught it. The examiner feedback here would be absolutely ruthless. 0 marks. The fatal flaw was the word swinging. As we established earlier, the suspended strip must be perfectly stationary first. If it's already swinging, you cannot accurately observe whether the second strip caused repulsion or attraction. Those small details in your practical descriptions matter immensely.
Which brings us to unlocking the examiner clue. It's time to fulfill that promise I made you earlier and escalate the stakes. So, the big secret is this definition right here, the gold leaf electroscope. Our source explicitly states this apparatus is used to detect charge and, critically, to distinguish between good and bad electrical conductors. If an exam question asks you to design an investigation to test if a material is a conductor or an insulator, or simply how to reliably detect the presence of a charge, mentioning the gold leaf electroscope is very often the hidden requirement to unlock the top band marks for practical evaluation. It's a total game changer. And now, the target grade bridge. This is the final escalation. You've got the framework, the phrasing, and the apparatus. But there's one final unresolved problem. Just look at the contrast in these command words. On the left, describe how to charge a strip. Now look at the right. Evaluate the use of an electroscope. You might have flawless physics knowledge, but the words describe and evaluate require entirely different ways of structuring your answer on the page.
Which leaves us with this really provocative question. If you don't know the difference between Cambridge command words, will your perfect physics knowledge still score 0? The harsh reality is, yes, it absolutely can. You can write a scientifically perfect paragraph, but if you merely describe when the examiner specifically asks you to evaluate, you will miss out on the top band. You must know exactly what these command words demand. To ensure your perfect physics knowledge actually gets the grade it deserves, you must watch the next explainer on command words. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Click the explainer on the right side of the screen right now to master those command words, and I'll see you over there.